In section 2.6, we're going to be looking at trigonometric limits, and so vital to this discussion will be knowledge of your unit circle, knowledge of your trig ratios like tangent equals sine over cosine, etc., and also some few key theorems. The first of these theorems that we're going to look at is called the Squeeze Theorem. The Squeeze Theorem actually makes quite a bit of sense after you look at it pictorially, but when you look at the definition it's not always so clear. So first of all, let's read through the Squeeze Theorem up here. It says, consider a function f of x that is trapped between two functions. The two functions that we're trapped between are between the lower and the upper, and so they're using L to represent lower, U to represent upper. So in this picture over here, here's my lower function, here's my upper function. In the picture below, lower and upper. And it says we're on an interval I, and so the interval I that we're looking at is just being between where this is graphed from on each of these. It says, in other words, the function is between the lower and the upper. So the function that we're always looking at is always between or equal to these lower and upper functions. And we can see over here in both of these graphs that that's the case. F of x is between the lower and the upper. F of x is between or equal to the lower and the upper. So all the criteria in this first definition of the Squeeze Theorem is working. It says if this is the case, the graph of the function, this is our function again, f of x, we have two different pictures here, lies between the graphs of the lower and the upper. Okay, then that's going to tell us something about the limit if the f of x function is squeezed between the lower and the upper. So this top picture right here, you can see that it's between, but it's not squeezed. This doesn't tell me anything about the limit. The limit here at C, we'll say is something like 7. The limit here at C might be 5, and the limit here at C might be 3. We can see that it's not squeezed between that 3 and 7 enough to try and predict what this value is in between at C. Now over here, notice that it's squeezed in this behavior that I can look at. And again, this is a hollow point here. I'm just trying to accentuate this. Because the limit of the upper and the limit of the lower are both equal to L, that means the limit of the in-between, or the function itself, is L as well. So that's the Squeeze Theorem. Now the problem with the Squeeze Theorem is coming up with this upper and this lower function that will work nicely. The best way to work on this is by looking at some examples. So let's go ahead and look at our first example. The limit as x approaches 0 of x squared sine 1 over x. Okay. Well, first of all, we use substitution. That means we just go ahead and plug directly in. And when we do that, we get 0 squared, because I'm plugging in for 0 here, sine 1 over 0. Well, the sine of 1 over 0 is actually off of this graph right here. As we approach 0 from the right, I have a limit of infinity. From the left, I have a limit of infinity. So this piece right here is basically saying 1 over 0 is undefined, therefore the limit does not exist. So we can't really take the sine of something that does not exist. So this looks like 0 times dne, basically. Okay, this is an indeterminate form. Indeterminate means to do more work. Well, the more work that we want to do here on this case is the Squeeze Theorem. Now again, with the Squeeze Theorem, the tough part is to come up with the upper and lower functions that squeeze the x squared sine 1 over x for this particular case. The best way to usually do that is to kind of build it. So let's go ahead and start with the sine of 1 over x. We know that the range of the sine function is between -1 and 1, so we can kind of start with that. Remember, the sine curve is always between -1 and +1. It doesn't matter what this argument is right here. Okay, the sine will always be between -1 and +1. Now, I don't need sine of 1 over x, though I need x squared sine 1 over x. So what we can do in our next step then is to multiply through by x squared. So you can see that we're kind of trying to produce the function of interest, and in so doing we also come up with some nice bounded values here. So it looks like these two functions, negative x squared and positive x squared, will squeeze this x squared sine 1 over x. Now, what does the graph of x squared look like? It's a parabola opening down. The graph of positive x squared is a parabola opening up, And this is kind of our unknown here. So let's go ahead and grab a maple graph of x squared sine 1 over x. So here's the graph of x squared sine 1 over x. Now remember, our parabola opening down, this negative x squared, it's probably going to fall somewhere in here. Positive x squared is probably going to fall somewhere up here. So it does indeed look like these upper and my lower, because remember this is called my upper, this is my lower function, do indeed squeeze x squared sine 1 over x. But let's go ahead and look and see how Maple plots that. Maple plots that similar to what we thought it would be. And so it does look like, it is squeezing that graph. So what do we do with the squeeze theorem now that we know we have an upper and a lower? And we've shown that we have an upper and a lower that squeeze this both algebraically like we developed here and graphically like we developed here with our graphs from Maple. Well, what the squeeze theorem says then, we have this negative x squared that we think, and we have shown, I guess, that is squeezing the x squared sine 1 over x. Well, what I do is I take the limit of each piece. I take the limit as x approaches 0 of negative x squared, and I take the limit as x approaches 0 of positive x squared. So we can see by plugging in directly we get 0 for both these limits. So the conclusion is then that the limit as x approaches 0 of x squared sine 1 over x is 0 as well. Because the limit of my upper function here is 0, the limit of the lower is 0, so therefore the limit of what is being squeezed by these two functions is 0 as well. So that's how the squeeze theorem works. But again, the difficulty is coming up with the proper functions, the upper and lower functions, to squeeze that middle theorem, or squeeze that middle function. Let's go ahead and look at two more important theorems that we'll be using. This first theorem 2 gives you two very important trigonometric limits, and we will definitely want to know these. So these would be a good thing to have memorized. Theorem 3, we're going to use this fact, but whenever you need this fact you can go ahead and look it up, but definitely these would need to be memorized. And I would say one more thing about these theorems, you should always put parentheses around the arguments of your trig functions. The book doesn't all the time, but it's important that you're consistent with that. Maple expects it, and I'm looking for that too when I'm doing grading. So these are a couple important trigonometric limits. Let's go ahead and look at the first one. Limit as theta approaches 0 of sine theta over theta. They say that this is equal to 1, and we've actually done this problem before when we first were looking at some limits, and we looked at this as an example that we graphed in Maple. So let's go ahead and go to Maple and see what the graph looks like. So here's the graph from Maple, and realize of course Maple does have its limitations as well. We know that if we plug 0 into this function, we'd have a hollow point here. So this point is actually a hollow point, it's undefined, but Maple doesn't realize that because it's just connecting points. So this is a good one to remember. Also our second one, the limit as theta approaches 0, and again you can use x with these two. Theta approaches 0 of 1 minus cosine of theta all over theta equals 0. Let's go ahead and pull in a graph here as well from Maple to see what we get. Now from this graph we can see we have a problem as well. If we were to plug 0 in at this point, this should be a hollow point, it's undefined. Now how could we verify that these limits are true? Well, we could look at both of these graphically like we just did. We could look at them numerically, plugging them into a table. And not yet, but in Calc 2 we'll have a method called L'Hopital's rule that will allow us to evaluate these limits very easily. But for now we don't have that. So we'll just go ahead and depend on that these theorems are true. So let's go ahead and work some problems based on some of these theorems and using our unit circle. So our first example, let's look at the limit as h approaches 0 of the sine of 2h over h. Now remember, you can check all of your answers in Maple, but you don't want to be dependent on Maple for getting your solutions. So the first thing we do is we plug directly in, and I get the sine of 0 over 0, which of course is 0 over 0. Indeterminate, do more work. Well, the more work that we can do includes a graphical approach, We could also look at this from a numerical approach and produce a table, or we can use this nice theorem that we have now. So let's go ahead and run up and grab that theorem that we're going to use. The limit as theta approaches 0 of sine theta over theta equals 1. That's the one we'll use. Now I rewrote this just a little bit to match, instead of theta I used h's. But we don't really quite have this theorem, if you'll note. We are missing a 2 here. We need the 2h, and we need a 2h. So this theorem does not apply directly. I'll have to manipulate it a little bit. So what we do is we say, okay, well this would work if I could substitute the letter u in here, let's say. So we could do a little bit of a substitution, and we could say the limit as h approaches 0 of the sine of 2h over, if this was a 2h right here, this would work perfect, because then the arguments would be the same for the sine and the denominator. Okay, and of course as we're approaching 0, whether it's h or 2h, that still goes towards 0. But you can't just arbitrarily divide by 2, you have to multiply by 2 as well. So what this ends up looking like is pulling that 2 out front, and then we're left with the limit as h approaches 0 of the sine of 2h over 2h. Now what ends up happening is this entire piece right here equals 1 by theorem 2, and that's how you should support that. So we're left with 2 times 1, which of course is 2. Now again, you can verify this using Maple as well. You could graph this function sine 2h over h and look what's happening near the origin, and it should be approaching 2. It won't equal 2 because it's actually undefined exactly at 2.